Good afternoon, everyone. Thank you for joining us. My name is Jing Qiu from Alibaba Damo Academy. I'm a hardware engineer, and today with me is Jiayan Qian from ByteDance. He leads some software optimization efforts, and I'm also presenting on behalf of my colleague Jing Qiu, and he is the principal contributor to this work. So today, we will walk you through our joint effort on the hardware and software co-optimization around the RISC-V Vector Instruction Set for the video codec workloads. So today's presentation will be organized into 4 parts. Firstly, Jiayan will share with us some of their insights when they try to optimize the video codec workloads. And especially, this will include some instruction set gaps for RISC-V. And I believe that their findings will provide evidence for us to do the subsequent hardware solutions. And secondly, I will introduce some of our Xuantie team's proof of concept work using the RISC-V vector fast-track extensions that are currently being processed in the community. Thirdly, we will detail some of our hardware-software co-optimization strategy designed to help video codec applications realize their full potential. And finally, we will show you some performance results. Okay, with that roadmap in mind, I'll hand it over to Qian first. Please.
Okay. I will go first. I'm Jiayan from ByteDance, and I'm from the ByteDance server software team. And our goal is to build the RISC-V software ecosystem for the ByteDance workloads. And the most important thing for us is the video transcoding and all video codec workloads. Okay, this is my part. The video codec libraries is very different than other application libraries. It has a lot of kernels that are implemented with handwrite code, handwrite assembly code. So and so it is for these workloads, the performance and everything. They will implement hundreds or thousands of different kernels for like this for very different platforms for x64, ARM, MIPS, and so on. This is a typical compute pattern of video codec workloads. It is usually load fixed pixel blocks such as 4x4, 8x8 lecture from 1 or 2 image frame and compute by each pixel. So this pattern is called that each row is a vector, and this row is it's a stride load, but not stride load by element, but stride load by vector. So the compute pattern is also calculated by vector, and this vector is a very small vector, not a 512-bit, but usually 128-bit or 256-bit. This is an example for sum of squared difference code. This kernel is calculate to load 2 pixels and then widening twice and reduction sum at the final. And you can see the first implementation. We try to follow the vector agnostic intention and use the large lmul. And because of this compute need to widen twice, so the lmul must become larger at the final. So that causes a very wide reduction sum, and this is cause a low performance at most of the platforms. But this is advantage for the VLAs for larger lmuls, because if the hardware implementation is based on VL, in this kind of code may be as performance as the like code like this. The second code is we just only change the lmul set to fit the 512-bit VLAN. And this code is changed a little bit. So this is also why our first implementation is developed like this. But we find that it is not good at the smaller VLAN hardware. So we are trying to implement this kind of assembly code. This code is using very small lmul and using the interwaved compute, like interwaved the compute instruction and the load instructions, so that can hide the load latency, and also this can get a narrower read sum at the final. So at the 128 VLAN, it may be better. And it is also a VLA code, but it must not good at the longer VLAN hardware. So this is what I want to say, that is VLA has a bottleneck. Maybe some guy will not happy at this slide. But I want to say the original intention of VLA is write once, run anywhere. It can eliminate scalar tail loops, and it want to use one code for any vector length on different hardware. And it want to perform scales with large vector lengths. But at the real world, especially practicing video codec libraries, it's become a problem. I want to say this: the more hardware, the more fragmented. We find that first, the benefit for VLA is not worked at the fixed kernels, because it not has that tail loop. The second is, as the last slide goes, the specific code for every vector length to get best performance. So it costs the libraries maybe need 3 or 4 times files as what ARM does, and also because of the memory layout of the video codec libraries, the performance is also hardly scales with large vector lengths. And the next gap is we find that the RISC-V 1.0 has several gaps here, and it is not that compatible with other ISA. And we raised this topic both at RISE and VectorSig last year, and happy to see now there are 3 fast-track proposals that will solve the most significant gaps. The first is the ZvZip to solve the in-register transpose proposed by Rivers. And the second is ZvABD extension to solve the sum of absolute difference. This is proposed by ByteDance. And the second is dot product proposed by Zvabd. And there is also some secondary gaps. One is something like mentioned in RISC-V 1.0 spec, but one is the sign saturate and narrow tone sign, and one is zero extend move from scalar to vector, especially for 16-bit. They need a more another instruction at ZvB to solve that. But I think this tool is not in the most critical parts. And also we find some other gaps these days. One is the extract vector from pair vectors, and the other is vector arithmetic by specific elements. And we can consider later. And next, Xinyu will introduce their hardware implementation and at hardware and utilizing the three fast track at software and get the performance result. And the second, Xinyu will also introduce their idea to solve solve VLA problems. Okay, Xinyu.
Hi, thank you. I will start with some ISA level optimizations. And Jiayan has noticed that there are several fast track extensions in progress for the RISC-V community. And although they are not ratified yet, but we have already support these instructions in our hardware. So we believe that it's a good proof of concept work, and we can show that these instructions can truly optimize the performance of the video codec workloads. And the first extension we'll talk about is the ZvZip. This extension enables structured data reordering inside the vector registers. And on the right side of this slide, you can see two of the new instructions from ZvZip, which is the Zzip even and VZip odd. Their names may have been changed in the latest version of the specification, so just excuse the maybe some small mismatch. And as shown in the left side of the slide, we show a flow diagram of a SATD operator. And this operator, as you can see, the element interleaving pattern in this operator matches the new ZvZip instructions. So this let us to do the required arrangement with much more fewer instructions. So in practice, we mainly apply the ZvZip instructions in the 4 operators shown above, and we can see about a 1/3 reduction in instruction count for these operators. And secondly, the extension we'll talk about is the ZvAbd, and it defines a set of instructions for some vector elements to compute the absolute values or absolute difference values. These instructions can be widely used in the, let's say, X224 or X264 or X265 workloads, because just as the SAD operator itself means that the sum of absolute differences. So we wrote these operators with some handwritten assembly to use these instructions, and we can see at least a 20% performance improvement. And finally, we'll talk about the ZvQ extension. Their function is somehow straightforward, as the name suggests. This slide shows one VQ dot instruction on the left side. It performs a partial dot product of 2 vectors of 8-bit signed integers, accumulating them in the partial sums into a vector of, let's say, 32-bit VD register. So with all these 3 fast-track extensions in use, we among the top 15 operators by runtime, we can see that more than 70% of the operators can gain performance from these 3 fast-track vector extensions. And this slide shows the cycle reductions for the top 15 operators by runtime. The result shows that the optimized ones can achieve at least 40% cycle reductions and the best one can show more than 80% cycle reductions. So these results show that the community extensions can effectively improve the video codec performance. And also, since these extensions are not ratified yet, please feel free to join the vector SIG and join the discussions. Okay, and thirdly, I will go further into our hardware and code software co-optimization efforts. Since the new instructions alone are not enough, firstly, we introduced a hybrid widest execution architecture in our hardware. And this optimization comes from an observation that in the X264 or 265, the parallel data bit widest is usually not very high. You can see from the table on the left, depending on their element widest or VL settings, an instruction may actually operate on only, let's say, 64 bits or 128 bits data. So this means that when our hardware supports a larger vector length, such as 256 or even higher, some computing resources can be idle in the pipeline and may be wasted. So to address this problem, our hardware dynamically adjusts the pipeline execution data widest based on the current VL or the LMA configuration. So if the parallel data bit widest can drive the data path at full widest, we enable a let's say dual issue structure as shown on the right side of the slide. But if the parallel data bit widest can only drive the data path at a half widest, then we can enable a quad issue structure. That means we can sustain a throughput of 4 128 bit instructions. Also, there are some more works we add to our hardware and software co-optimization, like instruction fusion, which I will not go further here. And we add some forwarding strategy promotion or tail data processing acceleration in our hardware. And also loop unrolling, this kind of traditional software optimizations can also be used here. But we should also point out that these strategies sometimes should be aware of the hardware capability to fully utilize the hardware pipeline. So finally, there's 2 slides of performance results. The first one, the baseline, is the LLVM compiler without using the newly defined fast-track instructions and use the auto-generated vector instructions. And we can see that with all the optimization methods we use, we just talked about earlier, the benchmark is the X264 and X265. They can reach more than 400% the performance of the baseline. And even we choose the baseline as when the baseline already uses some good handwritten assembly and the new vector extension instructions used in the baseline, we can see that using the hardware and the system level optimization methods in our system, we can see of about 49% performance improvements. And this is exactly the show that even with well-written software, system-level optimization can still have very strong potential. Okay, so that's all the contents we want to share today. Thank you.